Hello, I'm Kate, and in this video, we're going to be working on handling data. As a scientist, the ultimate table has to be the periodic table. This was conceived by Dmitry Mendeleev over 150 years ago. This was before they had found any of the subatomic particles. Yet using his table, he was able to group elements in two ways, by their masses and by their properties. What was most amazing about his table was that it then enabled him to spot missing elements, and he was able to predict what their properties would be. This enabled scientists to go and look for these missing elements, and when they found them, they matched Mendeleev's predictions. It's a massively powerful table. If you're working with data, tables, means, and uncertainties are going to be a key part of your skills. But there are conventions that you have to stick to. Tables allow you to find patterns, they allow you to spot anomalies, and they bring power to your data analysis. Let's begin by looking at tables. Okay, so here we have some data about temperature and the volume of gas that's produced in 30 seconds. It's the sort of data that you would collect in a GCSE rates of reaction experiment. I would like you to draw up a table to present this data. Make sure you stick to the appropriate conventions. Pause now. This is what your table should look like. In a table, we have rows and columns, and the headings show what's recorded in each column. Notice that your units go in your column headings. We usually bracket them. What you must not do is put the units with the data. That's totally unacceptable. It's also worth noticing that your data must be recorded to the same number of decimal places. So let's say that you were actually able to collect all of these to one more decimal place, and in some cases you had a 0.5 and in some it was exact. You can't just put the 0.5s in, you've got to put your 0.0s on the end so that all of them match in terms of the decimal places. Here we have no decimal places for any of that, so they all match. That's something really important for you to think about when you're doing a final check through of the tables that you've drawn up. Do they have the units in the headings? Are they all to the same number of decimal places? Is it appropriate in terms of conventions? Right, next we're going to look at calculating the mean. So first of all, why do you want to find the mean? Well, by calculating the mean, this enables you to reduce the variation in your data and get a more accurate value. To find the mean, you have to add up all of your data and divide by the number of repeats. But you must remember to watch out for anomalies in your data. More on that soon. So here's an example of a table from which you might calculate a mean. So we're saying that Vamika ran 100 metres 3 times. Each time, the time taken was recorded. So you've got your repeats here, you've got the time for each. I would like you to calculate the mean time in seconds. Pause now. So what you should have done is added up each of the times and divided by 3 because there are 3 times, giving you 14.2 as your mean. It's to 3 significant figures, same as the data. Let's talk about anomalous results. So before you calculate your mean, you need to check through your data for any results that stand out as not fitting the pattern, and we call these anomalies. We don't include them in the mean because they affect the value. Now, students often ask me when they're trying to find out about anomalies early on, they say, well, how do I know what's an anomaly? How much can it be out by? There is no set answer to that. You have to look at the data that you're given, and you need to look at the variation in that data. If they're all within 5 units, then something that's 10 units out would be an anomaly. However, maybe there's a variation of 20 units between them on average, in which case, well, it's 10 units out, that's not an anomaly. So it depends on the data that you've collected and how close the scattering of it is, and you have to take each case separately. The key thing is, don't go identifying lots of anomalous results. Typically, you wouldn't expect to have more than one in each sort of set of repeats. When you're then calculating your mean, having excluded any anomalies, do remember to reduce the number of repeats that you're dividing by. Okay, so if you had 4 pieces of data, one of them's an anomaly, you're then adding up the other 3 and dividing by 3, not 4. Right, so I've presented you here with a data table. So it's a typical rates of reaction sort of experiment again. We're varying the concentration of the hydrochloric acid and you're collecting different volumes of gas for each of those concentrations with 3 repeats. So a slightly more complex table. What I would like you to do is go through the table, identify any anomalies, typically we circle them to make them stand out, and then excluding the anomaly, calculate the mean for each concentration of hydrochloric acid. Pause now. So here are your results. These are the means that you should have calculated. Let's have a look at how I did that. Looking at the data, I decided that all of the data in the first row was a good fit. There was no data that stood out, no anomalies. In the second row, however, we've got a couple of units between 35 and 37. 28 is clearly too low, so that is anomalous. And in the final set, we have 41 and 43. 50 is clearly much higher than those, so that is anomalous. I then calculated the means for each by adding up the data, dividing by 3 for the first row and by 2 for each of these rows. I'm then giving the mean to the same number of significant figures as the data, giving 26, 36 and 42. Final bit for this video that we're going to talk about is uncertainty. When you make a measurement, there's always some uncertainty in your data. And by showing what the uncertainty is, it tells you the range within which the data lies. And we show this as the number plus or minus the uncertainty. It tells you about the accuracy of your data. Right, key bit of information here. The uncertainty is usually half of your smallest division on your equipment. So let's think about a thermometer. We've got divisions of 1 degree C. We record a temperature of 25 degrees C. This temperature could have been as low as 24.5, so half a division lower. If it was any less than that, it would have been rounded down to 24, so it can only be half a degree too low, or it could have been half a degree higher. Any more than that, and it would have been rounded up to 26. So that gives us an uncertainty of 0.5 degrees C in our data. So we record this as 25 plus or minus 0.5 degrees C. So telling us it could be half a degree less, it could be half a degree more. Some equipment will tell you the uncertainty in the measurements that you're going to make. And this is typically for equipment that makes a single measurement. Say, for instance, a volumetric flask or a pipette, where you don't have graduations that you can use then to give you the uncertainty. Once you have the uncertainty, we often like to represent this as a percentage uncertainty because this is more meaningful. It shows us by what percentage our data could be out. And that's basically telling us about the significance of the uncertainty compared to the reading. So let's look at an example. Imagine that we've got a measuring cylinder with an uncertainty of plus or minus 1 centimetre cubed. So we're basically thinking about divisions on it of 2 centimetres cubed. If you did 2 different readings using this measuring cylinder, the uncertainty is going to be much more significant in a lower reading, so say 5 centimetres cubed compared to in a higher reading of 50 centimetre cubed. The way that we work out the percentage uncertainty is you do the uncertainty divided by the reading times 100. So I would like you to have a think about taking the 2 volumes of 5 plus or minus 1 centimetre cubed and 50 plus or minus 1 centimetres cubed, and I would like you to find the percentage uncertainty in each of those readings. Pause now. So your answers should be 20% for 5 centimetres cubed and 2% for 50 centimetres cubed. What I've done is taken the uncertainty each time of 1 and I've divided by the reading, so 5 or 50, and multiplied it by 100. So we can see a 20% uncertainty in the lower reading is much more significant than a 2% uncertainty in the higher reading. We sometimes need to think about how we can reduce the percentage uncertainty. And there's two strategies that you might choose to undertake. One is to use the most accurate piece of equipment possible for your measurement, because that would reduce the uncertainties that you have in any readings. So here, for instance, rather than using a large measuring cylinder with an uncertainty of plus or minus 1 for a small reading of 5 centimetres cubed, we might have used a smaller one. Or we might have used a completely different piece of equipment to make that measurement, like a pipette, that would give us a much lower uncertainty. The second thing that you can do is make your readings as large as possible. If we have a look at the equation, because you're doing the uncertainty divided by the reading, if you make your reading bigger, you're dividing by a larger number, which makes your percentage uncertainty smaller. So that's always a good strategy to think about. Finally, we're going to talk about combining uncertainties. So sometimes when you're measuring a change in a variable, you make two readings, and this then means that you need to add together the uncertainties. So let's take a look at an example. Let's say we have a reaction where we're measuring a temperature change. You have a starting temperature of 22 plus or minus 0.5, and you have a final temperature of 38 plus or minus 0.5. We want to find out what the temperature change is, including the uncertainty. Pause now and have a go. This should come out as 16. We're subtracting the temperatures, and it's plus or minus 1 degree C. So you're adding together those uncertainties of 0.5 in each case. Let's just take a look at how this works. The lowest possible value you could have had with that uncertainty was 21.5 degrees C. The highest possible value was 38.5 degrees C. If we do 38.5 minus 21.5, that would give you a temperature change of 17 degrees C. That's the maximum that you could have got. Let's say the data was closer together. If we had 22.5 as our first reading and we had 37.5 as our second reading, when we do the difference between those, so 37.5 minus 22.5, that would give you a difference of 15 degrees C. So we can see what the maximum possible reading is of 17 and the minimum possible reading of 15. That is 1 degree higher, 1 degree lower than our measurement. So that is why we have to add the uncertainties to give us the correct uncertainties in our overall reading. So that's everything that you need to know about data analysis as your quick introduction. We're thinking about how we present it in tables and then how we go on to analyse it further. Next up though, in your following video, will be all about graphs. So thinking about how we can display our data so that we can see patterns even more clearly. If you were at all rusty on any of that today, please do try the consolidation exercises. Thanks for working with me. Bye.